when I worked as a postdoctoral researcher on a project on crayfish osmoregulation. We knew that the problem crawfish faced in fresh water is that their hemolymph body fluids are more concentrated than the lowest concentration of fresh water. So water will come into their body down a gradient. And ions will leave their body moving down a gradient. Most of their body surface is impermeable to both ions and water. The problem is their gills, which are right here on either side, have to be permeable to oxygen and CO2, and that makes them usually permeable to water and to ions as well. So that's the area where their biggest problem is. We found that they have 4 little tricks they use to be able to survive in fresh water. The first one is that they reduce the concentration of their hemolymph when you compare them to their saltwater marine relatives like lobsters. And that means that there's a smaller gradient for ion movement out and water movement in. They also have greatly reduced permeability over their whole body surface and their gills compared to their marine relatives like lobsters. Additionally, they have ion transporters at their gills, and they pump ions in against a gradient, spending a lot of energy to do that. And the fourth thing that they do is that they release copious amounts of dilute urine. That gets rid of that water coming in, but only a small amount of ions because it's so dilute. I drew it coming out here because they actually release urine right in front of their face, which seems like a disgusting thing to do, but they're pumping water across their gills and it moves forward and out right here on either side, and so it washes the urine away, so it's typically not a problem for crawfish. So this works great, and this is why crawfish are the largest invertebrate that you find in so many different freshwater areas around the world. But they run into a big problem, because what do crawfish have to do if they want to get bigger? Think about it for a second. They got to molt because they have an exoskeleton, so they have to shed that exoskeleton to grow. When they shed that exoskeleton, the new exoskeleton underneath it is soft and it's also permeable. That allows them to increase in size, but they lose a lot of ions and they take in more water than is optimal during that period. Well, we found that they have a couple adaptations to deal with the molt as well and still thrive in fresh water. What they do is, before they molt, they remove a lot of calcium from their exoskeleton. Then once they shed that exoskeleton, they consume it. They eat their shed exoskeleton, which is called an exuvium, and they regain all the ions that are in that shed exoskeleton. Another thing that they do when they molt is they pump ions across their gills at ridiculously high rates, higher than most fish are capable of. And a third trick they have is that calcium that they removed from their exoskeleton, they store it in their stomach as a gastrolith, or stomach stone. So it's a calcium carbonate concretion that they keep in their stomach after they molt, and then they dissolve it and they move all of that calcium to their new exoskeleton. And a calcium carbonate gastrolith looks a lot like this.